calculus, say we have a graph. So let's just say we have a graph. Let's just say our curve looks something like this. Calculus is just asking us what is going to be my rate of change and what is going to be my equation of the tangent line at a specific x value where the tangent line just slightly touches the curve. So a function f is differentiable at x is equal to a if the derivative f prime of a exists. A function is differentiable on an interval if it is differentiable at every number in the interval. 4 common ways for a derivative to fail exist are this. Okay. So why would we not be able to find the derivative in example number 1? Does anyone have any idea? Why would we not be able to find the derivative in the graph presented in number 1? You could be wrong, it's fine. You could be right, and that's also fine as well. Yep, there is a tangent problem, which means that we have something over here called where our slope is undefined because of this vertical line. Okay, we have a vertical tangent, which means a slope of a vertical line is always undefined. Okay. So slope of vertical line is undefined. Okay. So for number 2, why can we not find the derivative, or why does the derivative not exist for number 2? So why would the derivative not exist in graph number 2? Remember the definition of, so remember to find the slope in calculus, we find the slopes of what? Straight lines or curves? Yep, it is, but there are some times where it's not differentiable. So if it's not differentiable, that means the derivative fails to exist. And remember with calculus, we are always finding the slope of what? Straight lines or curves? Curves, right? So what is the problem with number 2? It's straight. Okay, there are no tangent lines in number 2, which is the problem. Okay, so because there are no tangent lines, that means it's not differentiable and the limit fails to exist. Okay, for number 3, what is wrong with number 3? Why can it not be differentiable, or why does the limit fail to exist in number 3? Yep, the slope is undefined. Okay, you have this vertical tangent here, and as we know that the slope of a vertical line or vertical tangent, it remains to be undefined. And then last but not, the last one's pretty obvious. Why does the derivative fail to exist in the last one? It's not continuous, okay? So which means there's no tangent line at the point x is equal to 1. So there is a hole. If we have a curve that doesn't have any vertical tangents, we should be able to draw a tangent line at every specific x value. If we can't do that, then we are not able to differentiate it. So it is possible for a function to be continuous at a point and non-differentiable at that point. In the first three graphs above, both functions are continuous for x is the element of all real numbers. But because, although it's continuous, because of the characteristics that it has, we cannot find the derivative for these specific examples. So again, we're going to take the same example. We want to show that f of x is equal to the square root of x is not differentiable at x is equal to 0. Okay? What means that there are no tangent lines. What this means is that either there are no tangent lines or we have an undefined slope. So as you guys remember, we know that square root of x is just a b. And we've already come to the conclusion, based off our previous examples, that it is not differentiable at x is equal to 0. However, we have to show that using our definition of a derivative. Which basically means that we have to show our first principles and see if the limit exists or doesn't exist. So again, we're going to start with f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So limit as h approaches 0, we know that we want to figure out if it's differentiable at x is equal to 0. So I can sub in 0 for x, so we get absolute value of x plus h minus the absolute value of x all over h. So let's sub in x is equal to 0. So I get absolute value of 0 plus h minus the absolute value of 0 over h. And I'm left with the limit of h approaching 0 of the absolute value of h over h. So again, when we prove that the absolute value of x, the limit didn't exist, we did the absolute value of x is equal to x if x is greater than or equal to 0, or negative x if x is less than 0. So the same thing can apply to our absolute value of h. It is positive h if h is greater than or equal to 0, and negative h if h is less than 0. Okay? So we can take that same concept and apply it to proving that it is not differentiable at x is equal to 0. So again, we have our limit of h approaching 0 of square root of h over h. So again, we want to find the limit as h approaches 0 from the right and from the left. So the limit as h approaches 0 from the right, our absolute value becomes positive h over h. So if I were to simplify h over h, what does that give us? What is a number divided by itself always? It's going to be 1. Now we take that same idea and apply it from h approaching 0 from the left. And according to our piecewise function of the absolute value, as h approaches 0 from the left, we get negative h over h. And what does that give us? Negative 1. Perfect. So, is f of x equal to the absolute value of x differentiable at x is equal to 0? Yes or no? No. So therefore, the limit as h approaches 0 of h, of absolute value of h over h does not exist because 0 from the right and 0 from the left don't give you the same value, which means that it is not differentiable. So again, this is just another way of using the definition of a derivative to figure out if something is differentiable or not differentiable. So for example, 2, we want to state the domain on which each function is differentiable. So as you can see here, we have x is equal to negative 3. So what would my domain be on which I can differentiate this function f of x? At what x values can I differentiate this function? Okay, xer such that what? Yep, so we can differentiate this on all the values of x in the real numbers, but x cannot equal 3 because we have a vertical tangent at x is equal to 3. Okay, how about the next one? Where is this function differentiable? On which x values is b differentiable at? Yep. So we have a vertical tangent. So we can differentiate that x is an element of all real numbers such that x cannot equal to 4. Okay, so see, some of you may argue this. Remember the example where we had this thing right here? The reason why that was not differentiable is because of this corner over here, okay? If we didn't have that corner, then yeah, it could have been differentiable if we just had the straight line over here or the straight line continuing down there. But because of that corner, it did not make that specific function differentiable. So for the line y is equal to x, where is it differentiable at? It is differentiable at all of the x values in the real number system. When we start doing derivatives and their laws, you're going to figure out that the derivative of a line will always give you a constant number, okay? So for example, the derivative of y is equal to 2x, okay? What would the rate of change of the line y is equal to 2x be? 2, okay? Which means that the derivative of y is equal to 2x is going to be 2 because the rate of change is always going to be 2 no matter what, okay? Because it's not a curve, there's no real change in the slope at certain points, which is why the derivative of a line is always going to be a constant number. And last but not least, for D, where is my graph differentiable at? At what x value? So Ian, at xer such that x is greater than or equal to 2. Okay. However, we don't know if this point's included, so we can just assume it's just greater than -2. All right. So we're going to move on to the next page. So sketching derivative functions. So we know that the value of the derivative f at x is equal to a of f prime of x can be interpreted geometrically as the slope of the tangent line to the graph f at the point a and f of a. The slopes of the tangents at various points on the curve y is equal to f of x give the values of f prime of x, and we plot them directly beneath the graph of f. In particular, we get the x-intercepts of f prime of x from the local max and mins of f, where the tangent lines are horizontal and have a slope of 0. So without doing any math, and by using this definition, we want to sketch the graph of the derivative of the function f of x is equal to 1 over 4, x plus 4, x minus 2 squared. So at what x values are my slopes 0 for this cubic function? At -2 and 2. So here my slope is equal to 0, and here my slope is also equal to 0. Now what the definition is saying is that the x-intercepts of the derivative are going to be where my slope is 0 for the original function. So if I were to graph my derivative, I would have my x-intercepts at -2 and +2. And now to get our y-intercept or our vertex, we just take -2 and add 2 to find the middle, which is 0. So we sub in 0 for x. So we get So our derivative for x cubed is going to be x squared, okay? Which means that we're going to have a upward opening parabola. So our derivative function is going to look like this. I'm just roughly sketching it. It's going to be a parabola that opens upwards. So this would be y is equal to f prime of x. Okay, so this is just a rough sketch, and that is what your derivative would look like. So y is equal to, or f of x is equal to 3x squared. X to the power of 3. F prime of that, or the derivative, would be 3x squared. Okay? And if you were to find the next derivative, it would be 6x, and then the derivative of that would be just 6. But we'll get to that at a later point in time.